Dear friends, welcome to another very exciting edition of Data Science Tutorials. Myself, Dr. Suptik Mukherjee. Today's topic is logistic regression. But before I move into the topic, I have a small request. Please don't forget to subscribe our channel. We put a lot of hard work and effort in creating these videos. If you subscribe, it will motivate us significantly. Also, the Jupyter notebook that you're using today, uh, including the code that you're using, uh, will be uploaded in the GitHub repository, the link for which is provided in the description below. Now, those who are new to the channel and those who have subscribed, uh, for we would like to inform you that on the beginning of November, we are starting a course on data science for preparation of interviews. Um, those who want to join the course, please let me know through email, and we'll figure a way out how you can join the course and we can discuss the details. Now, coming to the topic, logistic regression. So what is a logistic regression? A logistic regression is a supervised learning algorithm. Why it's supervised? Because it's a level data specifically designed for binary classification tasks. Now, why it's a binary classification task? It means that either it's a 0 or 1, right? So, and we have to predict one of the two possible classes based on input features and label training data. So now let me show you a level data set first, how it looks like, right? So for example, here I have a data set, and this data set converted into data frame, it shows various features, right? But you see here it shows a spam indicator. So whether it's a spam or not a spam, that's labeled. And these are the various features. Now I want to create a model whereby I can predict whether it's going to be a spam, which is say 1, and whether it's going to be a not a spam, which is 0. And to do that, I fit a sigmoid function. And along the sigmoid function, I get the probability, that is the 0.1% probability, that 10% probability, 0 probability 0.1, 10% probability that it is 0, or it's a 90% probability that is going to be 1, that is going to be a spam. Okay, so that's the kind of problem we are dealing with. That's why it's a binary classification task. Okay, so now what I'm going to do is I'm going to explain the maths in details. You may skip this part completely, not a problem, but get some idea, some understanding of how the math looks like in order to tackle this problem of logistic regression, right? So first of all, this function that you are seeing here, the sigmoid function. This sigmoid function is 1 by 1 plus e to the power minus z. Okay, is a function of z, and this is how the sigmoid function looks like. Now, this is mathematically how it looks like. Now, what is z? So this sigma z is between 0 and 1. It's giving the probability, right? And what is z? Z is the features. Is the input features, combination of all the input features with weightages and or parameters. Now our goal is to find the value of the parameters. That is, z is b naught plus beta 1, beta naught plus beta 1, x1 plus beta 2, x2 plus beta n, xn. Our goal is to find beta naught, beta 1, beta 2, and beta n. Now, how do you do that? To do that, what you have to do first is that, because you see that z is a function of this x, right? So we can write it as hx, right? So now hx, we have to find a cost function, and the cost function looks something like this. Where is it coming from? So say yi is the level 0 or 1, and xi is the feature data point, then hxi is the probability, right? So now we start with the Bernoulli's distribution, where the likelihood of a single data point, which is xi yi, is L beta h xi yi, and 1 minus h xi, which is just the opposite of it, right? 1 minus yi. So you see here, when hxi is when y is 1, hxi is um, so hxi is a probability, and this yi can be either 0 or 1. Okay, so if yi is 0, then what happens? This one is 1, and this one is 1 minus hxi. And if yi is 1, then this is 1 minus 1 0, which is this one is becomes 1, and you have hxi. Okay, so when yi is 1, then it is hxi. When yi is 0, then it is 1 minus hxi. Fantastic. Now I take the log of this. So when I take the log of this, what it becomes, yi dot log of hxi 1 minus yi log of 1 minus hxi. Okay, not that difficult. Now I add a negative to the whole thing because we are trying to minimize the cost function, and therefore the cost function becomes this. That's for 1 point. Summing over all the data points, I get, and taking the average, then this is what I get, like sigma y is equal to 1 to m over all the data points, and 1 by m, taking the average. Now this is the final form, the logistic regression. Now I go to the how to find the beta. So if I have beta j is beta j initial minus alpha, which is the learning parameter, right? And then partial derivative of the cost function j beta with the beta j. And how do I get that value? How do I get j partial derivative value? So what I do is, it will come something like this, and where xiga is the value of the feature xj for the ith data point. But how do we get it? So I know this is my j beta, this is the cost function, right? And then we are trying to get the derivative. So when I try to get the partial derivative, what I get is yi divided by hxi minus 1 minus yi divided by 1 minus hxi, and then the partial derivative of hxi with beta j. Okay, now uh, when I what is this value? This value is there's partial derivative of hxi with respect to beta j is hxi 1 minus hxi and del beta j of this whole value, which is of beta naught plus beta 1 x1 plus beta I1 I2 ij and so on. Now if I simplify it, okay, now coming back to where we were, we are trying to take the partial derivative of the cost function. And why we are trying to do that? Because we want to get the this value, right? We want to get this value j beta by j beta j. So the gradient descent is going to provide we're going to optimize the beta is used to minimize the cost function by updating beta. So beta j new is beta j minus alpha, the learning coefficient, and then the derivative of the cost function. Okay, so what is the cost function? The cost function is this, and this is the cost function. So you have a partial derivative of hx, which we are trying to figure out. So what is hx? This is basically partial derivative of hx is hx minus 1 minus hx, and the partial derivative with respect to beta j for beta naught plus beta 1 xi1 plus beta 2 xi2 plus beta n xin with respect to beta j. So this value we are calling it xij. Therefore, this simplifies to hxi 1 minus hxi xij. If we substitute this value into this partial derivative, then what we get is hxi minus yi xij, and if we take all over all the points, I is equal to 1 to m, and the average 1 by m. And from the gradient descent, as I explained before, we will get the new value of beta, updated value of beta, which we are trying to get after optimization. Now, another terminology that you need to know is confusion matrix. So we are dividing in logistic regression, we are dividing the data into training set and test set. And then we are making some predictions. Now, based on predictions, we are trying to see how many of these predictions are correct. So if you make the total predictions 1 plus 2 plus 3 plus 4, when it is actual negative and the predicted value is also negative, that means that prediction is correct. When it's actual positive and predicted value is also positive, that prediction is correct. So how do you know the accuracy score? The accuracy score is 3 plus 4 divided by 1 plus 2 plus 3 plus 4. So now if we look at the read the data set. So the data set, if you try to read, the data set is spam underscore email underscore dataset.csv. We use the pandas to read the data set, read underscore csv, and we print the header file, the dot head function. We use the dot head function, so we get all the features, including the one you see at the end, which is the spam indicator, which is 11101. So it is coming as a binary, right? So if we now try to write the code for the logistic regression model, we first import the libraries pandas as pd, scikit-learn linear model, import it as logistic regression, scikit-learn model selection, import as train test split, scikit-learn preprocessing, import as standard scalar, scikit-learn metrics, import as confusion matrix and accuracy score. So now this is my CSV file, spam underscore email underscore dataset.csv. Using the pandas and the read underscore CSV function, I create a data frame, data original. From the data original, I select these columns and store it in a new data frame called data selected. Now I using the dot describe function, I print the summary of the statistics for this data frame, and then I use the correlation function to get the correlation matrix between the different features. Okay, and then what I do is I extract the features and the target. So target is the last column, which is the spam indicator. The features of the columns I want as the features, and then I split the data into training data set and the testing set, and I use the train test split function to first provide the target and features in the target as the parameters, and where the features and target are coming from is coming from these are the features in the target, right? And the test size is zero point 0.3, which means that 70% of the data is for um, for for the training, and 30% is for the testing. I also use standard scalar. Why you are using this standard scalar? Because it's a, first of all, this is an instance of the standard scalar class, and I use this standard scalar so that we can have a mean of 0 and a standard deviation of 1, standardize the features. So this is a common pre-processing step in machine learning to ensure that all features are the same scale. Okay, that's why I need this thing. So scalar.fit transform, what does fit transform method is used to both compute the mean and standard deviation of the training data and scale it accordingly. So this is all for scaling. And then transform method is used to scale the testing data using, so this is for the testing data, use this transform into the mean and the standard deviation, use this scale the testing data using the mean and standard deviation computed from the training data. Okay, so I have everything scaled down, and then I create a logistic regression model. So the logistic regression model is going to have 200,000 number of iterations, because I, so high iteration is to ensure that the optimization of the algorithm has enough iterations to converge to a solution. And c is equal to 10, it comes to something called regularization, and regularization means it leads to overfitting or underfitting. That means if you are overfitting, means, so if c is less, then you are penalizing the model for using one particular feature to fit the model well. You are making it less complex, and you're preventing the model from becoming too complex, and then it fits the training data extremely well, uh, but is not generalized well to unseen data, which is basically overfitting. But then when we have c is less, and I very specifically mentioned this. Now coming to this c, basically if the c is small, then it is going to lead to something called underfitting. Underfitting means that you are penalizing the model for selecting one feature to fit the whole thing. Or, in other words, you are penalizing the model to have very complex decision boundary. So, its decision boundary is going to be simple. But if C is too high, then you are asking the model to basically have a very complex decision boundary, tight fitting, or you're using the features very features uh, to fit the model too closely. So what you are trying to do here is, so that will lead to overfitting. So what you are trying to do here is, you want neither overfitting nor underfitting, but um, if you are sure about the data, then you may try to do overfitting. But if it is too noisy, then you may try to avoid overfitting. Okay, and I've written out all these things deeply here in details. Um, Appropriate to have a large quality training data. For so when C is higher value like 10, it means that you are prioritizing fitting the training data closely. This which is a weaker regularization. This can be appropriate. So the regularization, if C is less, the regularization is stronger. If C is more, the regularization is weaker. That is regulation weaker means that you are penalizing less the model, less regularization, as simple as that. This can be appropriate if you have a large amount of high quality training data and you want the model to capture complex patterns in the data. Okay, so this is a very area of discussion we can constantly have about what value of C will be best to use. But now let's fit the model to the scale training data. So when I fit the model to the scale training data, I use the scale test features train and the target train. Okay, and then I go for the predictions. For predictions is the features um, test scaled, which is features test scaled is when I use the fit transform, right, to scale it. Okay, and then once this is done, I create the confusion matrix, which is the target test and the predictions, and then I go for the accuracy score. I use this function, and that is going to have a two parameters: target test and the predictions, same as a confusion matrix, right? And because it comes from the confusion matrix, the accuracy. So first of all, what I get the dot describe the summary of the statistics, the mean, standard deviation, maximum, 25%, which part of the data is 25%, below which 25% of the data lies, below which 75% of the data lies, and this is the median. Okay, um, and then I go to the correlation matrix, the correlation between the different parameters I get here. So you see attachment is 1, spam indicator attachment is 0.01. Let's look at something very high. I don't I see 63%, that uppercase and uppercase count, word count and uppercase count has a high correlation of 63%. Similarly, nothing much to look here. They literally have very little connection between them, each other. That's what this data is telling me. So I get the confusion matrix. I have 443 correct predictions plus 466. These are the total number of 443 plus 466 correct predictions. That comes to accuracy score of 50%. Actually, accuracy score of 50% is not a very good one. And why is it so? I tried a couple of things. I tried changing the C value, the overfitting and the underfitting, to see if we can get a better. Let's go to that C value. C value we can change to say 1. Let's say something very small. That means we have more regulations. if you are trying to fit too carefully, right? If you run it, I still get 50%, so it's not being affected much by this. Can you change the training set to say zero point 0.4? You run it, we get even less, 0.49%. 0.25, we get to something like 51%. Okay, so minor change we are getting. Um, so maybe we have to do some other model to fit it, but this doesn't seem to be the best way to fit it. Um, but then what we do is we try another data set, and this data set is a credit data, which is basically whether somebody can give back. So let's see what we have. That if you just run it, and so you see you have income, age, loan, and the possibility of the default. Okay, so that's three parameters, three features, and the one target. So here we do exactly the same thing. We use the read underscore CSV to read the data, create the data frame data, and then drop all the nan values, not a number, where whichever row it is there, drop na, and then we print the first five rows. We use the summary statistics. We describe that correlation matrix with dot core function, and then we use the features and the target, um, features and the target, and we use the, okay, just a minute, we use the training set and the test set with the train test split. Okay, now we have the data set being split into features train and target train, features test and target test, the training set and the test set. And then we use the logistic regression to create the model. We use the, we fit the model using the two parameters, features train and target train, and then we predict the model. We do the predictions using the features test. And once we have the predictions, we use this target test and the predictions to create a confusion matrix. Same way we use the target test and the predictions to create the accuracy score. And then if we run it, what are you going to get? Look, one thing is, first is, if we go step by step, we have the summary statistics, which is basically, so this was the dot head, right? Then summary statistics, which is giving me the summary of the statistics: count, mean, standard deviation, maximum, and so on, mean, maximum, and so on. And then it's going to also give me the correlation matrix. So client id is 1, but you see where else the correlation is high. The loan and the income is correlation is 44%. Then the default and the age has a negative correlation of 42%. That means higher the age, lower is the chance of default. And the loan and the default is at 37%. So very interesting statistics data we are getting here. And then we create the confusion matrix. That means 512 positive, 512 plus 45 correct predictions, 8 plus 35 wrong predictions. So totally it is 92% accuracy score, which is pretty good. So that's the kind of thing we are looking for in an ideal case, that we have a 92%, 90% accuracy score, 70 to 90%. But in case we do not get that, that means there's some, that is, the model is not the perfect one. Okay. So that's all we have here for the logistic regression, and hope you like the video. Our subscribers, to let you know that we are starting a course in the first week of November on data science, and for the interviews, as well as the entire course will be provided to you at a affordable cost. So those interested can write back to me, and before the classes start and the seats gets filled up. Thanks for watching this video. Do subscribe, and happy learning.